For the break, we have discussed NOMA-based cooperative relaying scheme. In that relay, we have considered the half duplex relay. Due to that only, transmission is going to the next level, next transmission time slot. But here, in the next work, what we have considered is the relay node has a full flex relay. Okay, we can able to receive the data and transmit the data simultaneously. That provision we have taken. Here, why we are going with the full duplex cooperative relay is to further improve the data rates and energy efficiency. We have considered the relay as a full duplex. Due to that full duplex relay, there is no need to waste the one more extra transmission time slot. That too, recently full duplex cooperation, full duplex communications with the antenna diversity have gained the attention due to improvement in spectral efficiency and throughput and the reduced latency. This is one of our design constraint. Accordingly, we have used. It enables here the relay node is enabled with the concurrent transmission and reception of signals. Here, source want to transmit the simple X1 and X2 to the destination. In between source and destination, there is a relay node is there. Now what it is doing, it is combining both the symbols X1 and X2 in a it is doing the superposition theorem and superposition principle, and it is transmitting the signal to the destination. Due to the broadcasting scenario, relay also can able to receive. While receiving itself, the relay will apply the successful interference cancellation, and after decoding the signal, it will transmit back to the destination. Okay, here the relay we have considered is a duplex relay. What it can able to do is it can able to do simultaneous transmissions and receptions, simultaneous transmission and receptions. So this work we got published in the Engineering Science and Technology and International Journal published this year. Okay, here at the destination node, first at the destination node is receiving the signals from the relay node as well as from the source node. What it will do, it will use the maximal ratio combining technique to combine both the signal. If you apply a maximal ratio combining signal to noise ratio, for signal X1 is given equation over 24. Then if decoding when you decode the express symbol, when you decode two symbol, you here it's translation. You will not you can just assessing this. Start by using the theta here. Theta theta is like a imperfect enthalpy factor. Based on this is equation number 22 and 23 is SSR that X1 SNR for X1 symbol and X2 symbol and 20. Similarly, equation QS stands for X1 X2 and no. Okay, the same thing. I am going to find out the minimal achievement rate. It is going to the equation 25. Here I need to find out the expectation. This expectation is nothing but my aim is to find out the channel probability density function. First, find it probability density function. Then we have this equation number 26. That is another mathematical expression for recording rate for signal itself. Okay, now we will come also. Like here, for suppose if I am transmitting some signal, if you are putting some load, length, total power is not sign equal the signal. Okay, the condition will consider as a what is where when we bring the signal is less than the preferred number, the condition is we are considering that the obvious probability is the some mathematical analysis. We found the equation number 27 is the voltage probability for single exon. Then here we are finding one more metric called energy efficiency. Energy efficiency can be calculated by using equation number 28. Here CX1 and CX2 is the achievable channel rate and PX1 and PX2 is the outage probability of single X1 and single X2 and there is a total power consumption. Here source and relay is transmitting less than equal times power transmit needed and source and relay and destination is usually in the sequence. That's why two times receiving power is given. Based on that equations, we plotted the ergodic rate. Like ergodic rate is plotted with respect to the distance between source and destination. When there is equal perspective, obviously this thermal capacity. From here, we consider the impact of self influence. Okay, how much here the relay is like a full duplex relay. While receiving, it is transmitting. People have only self-interest is coming. When there is increase in that self-interest is coming, then the water, the advantage will drop from the duplex relay. There is drop decreasing. The increment of the channel capacity is decreasing due to the increased self-interest. Here, these are the plot counters for influence between certain destination. Okay, here when there is distance increase, then outage probability is gradually going down. Okay, we are unable to receive the signals from. Okay, it's all in name is the X1 symbol is dotted line is the X2 symbol. These are the outage probabilities for X1 and X2 symbols. The remaining is for half duplex cooperative relay scheme also we have found. The better voltage probability you better improve voltage probability we are waiting for X1 symbol because here we are applying the maximal ratio combined technique. Now when coming to the energy efficiency also with respect to distance, energy efficiency is increasing. And if there is an impact or if there is a safety occurrence in the whatever the advantage we got, that is decreasing. The channel energy efficiency is decreasing. In the same thing, we have analyzed input of SIC also. When at the at the relay, while applying its transmission interference cancellation, if there is any interference again is here the ergodic rate is decreasing. Okay, whenever there is high then low half duplex cooperative NOMA. Okay, it is performing very low and it is underperforming the half duplex NOMA here. Similarly, we have plotted outage with external source. Here, we are getting performance in the cooperative NOMA. If there is an increase in the SIC, then the drastically down. That is only applicable for exclusive also. Then energy efficiency we have plotted with respect to with the SIC. When there is an increase in imperfect SIC, the energy efficiency gain also is increased. Okay, after that, what we did, we have taken one objective function. My objective function is to maximize the sum rate. Sum rate here is nothing but sum achievement for extension we want to maximize this with this instruments. Here, alpha is nothing but power allocation to the X2 symbol and F is the frequency. Based on that, we have applied optimization. We use particles from these are the non-optimal ergodic rate, and this is the optimal ergodic rate we have achieved. Even little bit improvement in ergodic rate in underwater, that also is good signs for underwater operational domain regions. Okay, here the observations are like the results show that full duplex cooperative relay NOMA scheme achieves superior ergodic rate and outage probability performance over other existing schemes. However, the performance is mainly degraded present impact of residual self-interference and successive interference cancellation. Later, in the next work, what we are doing, we want to improve the energy efficiency. Further, we consider the energy harvesting technique where we have considered the shifting technique. Here is like a simultaneous wireless information and power transfer technique. Uh, we are enhancing the energy efficiency. Here, from this figure, we already understood that uh, uh, from this figure, we have already understood that underwater acoustic sensor networks are mainly the path loss is mainly dependent on the transmission frequency and the distance. Due to that, what is happening? Some lower frequencies can travel for the longer distances. Higher frequencies can travel only for the shorter distances. With that, what we can able to understand is the bandwidth available for short communication is larger and for long communication is lower. High frequencies it will reach to the longer distance. Low frequencies can reach. Due to that, there is a bandwidth preference is there. The bandwidth for long is larger for shorter communication and lower for longer communication. As a result, here user the transmitter receives higher bandwidth and far user less bandwidth. Okay, we have taken that as the advantage and we are using additional bandwidth of the user also. This one here this relay is like a half like relay. What it is doing, like whatever the power it is receiving in the it is on the remaining 1 minus rho amount of energy it is using for in information processing. This splitting is called simultaneous wireless information and power transfer. This is here energy harvesting and the information decoding both are is happening at a time. Okay, based on that, we have based on that here how much power we have harvested. Okay, in this technique, user one is the near node. That is a delay node. It will do the energy harvesting. User one will do the energy harvesting based on the power splitting shifted where row portion of this energy harvesting remaining 1 minus row portion is used for the information decode. We can look for human energy harvested. That is gives me equation number 13. Okay, this is the energy harvested at the relay node. Okay, and in, obviously we understood that relay node is getting extra bandwidth. In the bandwidth, how much energy we can harvest? That is given with the equation number 31. This is the total energy harvested at the relay node. That is given by equation number 32. This is sum of 30 and 31 equations. Then source will transmit X1 and X2 symbols at a time. Then the signal received at user 1 is given by 33 equation. Based on that 33 equation, for decoding X1 symbol, typical SIMR, where X1 symbol power we are using as a desired power, remaining we are using like a, we are taking like a interference power. Wow, this fragmentation pass.
So fast cooking.
What's that? That's not any BS or some names are seen last week. Can you see? That have BS in the session. That's it. Very calculation. I got it back and out. Right. In another circumstance. One day, you know, you should do. Here, equation number 34 and 35 we choose the design of symbol x1 and symbol x2. Then you choose. The bar user. The signal is given the equation number 36. It will receive both x1 and x2 symbols. While decoding what about the SNR means, that is given by equation number 37 and 38. We will do the SNR for the symbols x1 and x2 at the user code. In the enhanced Nova, what is our contribution is like the harvested energy. Here harvested energy is based on the energy harvesting, like by using the Swift technique, and in additional bandwidth also we are transmitting some extra power. With that, here the energy harvesting is decided. Okay, with harvesting power, we will transfer the explosive symbol again to the power user. That is given with the equation number 39. This is the SINR for explosive symbol. It is given in the equation number 40. Like the power user will receive symbol x2 from relay node. This is from relay node and this is from the source node. It is receiving the signals. We are applying the diversity technique, selection diversity technique. In this we are using maximum selection diversity, maximum of SNR using SNR. That is given in the equation number 41. And in the next scheme, what we have considered that the shift we have considered like the time switching speed. Here the relay node what it is doing. Some amount of time it is using for the energy harvesting. Remaining amount it is using for remaining amount of time it is using for the signal decoding. Okay, this technique is called time switching. Based on that, we have found how much energy harvested at the near user. It is given with equation number 22. And again, in additional bandwidth, entire time slot you can able to harvest the energy. The summation of both will give like total energy harvested by the user. And the here the NRs for symbol x1 and x2 the user one is given with 44 and 45. And received signal at user 2 from the relay. One relay the amount of energy harvested, with the energy harvested power, we will transfer the x2 symbol to the power user. That is given with the 46 equation. With that, we found the SINR for x2 symbol 47. Again, power user what we will do? Do the selection diversity technique, maximum of SINR given in the 45 equation and SINR given in the 47 equation that you do. By using those SINRs, we are calculating the ergodic rate. From this we can easily understand that improved power splitting technique is giving better performance when compared to the power splitting. Thus, we are getting the additional bandwidth to the real user. The use additional harvestable product. We are getting the better therapeutic review. You even in time switching also will available in the underground. In the next one, what we are considering is we are considering the cross layer designing based on the Aloha norm. In this, mainly in physical layer, we have considered like Nova. In math layer, we have considered like Loma. When we went for this is recently cross dimension and advanced layers. Conventional engineering CDMA are inefficiently inefficient multiplex from purpose. So you we already discussed about minutes. Long propagation delays. Okay, that's why we research the source lead in you another access one of the easy you use map another one is map layer then the channel utilization is very less. Channel utilization is probably we are implementing the Noma in the physically. In the power of Noma, we will get the better map layer utilization. In this figure, what we are doing, we come to entire transmission range of transmission area into different regions. This is like region 1, region 2, region 3, like region 8. Now in each region, if one node is transmitting with the different power level, it is over a physical physics speaking. Suppose R1 R1 node region signal will receive at a higher power. Next R2, next in the middle, and from the far region, the power consumed at the AEV is less. Now, AEV is retrieving the power at the resist. I know all the first thing. That is Amarma. It is basically the math lesson which is Amarma and in physical is Roman technique. And here in all the symbols will receive at the same time at the AUI. Okay, this is for reason 3 and the reason I. This is reason 1. Number 9. Because propagation remains very less. If you start the data transmitting, it's important will come here. For reason 2, we will wait for next time. Somewhat less compared to the reason 1. To start the transmission at the section. For reason, start the transmission early so that all the signals will come at the same time and it can do the SIC at the AUV side. Okay. Now here we are mainly focused with the we are mainly focused with the finding the good. Okay. So for finding the good, what we need MAC layer utilization. MAC layer utilization is mainly going to success problem. Here equals to number 48 will give M number of flows that should be done. Okay, M number of flows that is the channel is due to 48. Here we assume that all the nodes are following independent and independently distributed Poisson's law. Accordingly, 48, when the surface figure when there is one transmitted that takes successful. When M is equal to 1, then the successful of probability. Accordingly, finding the magnitude Here, in our code, now, in our case, we have written the regions, this area into several regions. In our case, multiple false is fine. It won't be a collision because AUV is applying the SIC technique. Accordingly, the result probability have increased. Maybe sometimes from region one node is transferred. Another time, region one and region two, one node is transferred. From all the regions, maybe sometimes one node can transfer. When the when multiple transmissions are happening from same method, that we are considering that as a collision. Accordingly, we have found all the combinations. Based on the combination, the equation number 3 will form. By using 53 success probability, we found the MAC layer utilization. Based on the MAC layer utilization, the that is given with the equation number 5. We have plotted the results. Here, MAC layer utilization is plotted with respect to the upturn rate. This one analyzed with the effect of number of nodes also. When number of nodes are less, we are getting better utilization. With increase attending, but if less number of nodes are there, then they will get less chance reasons. When there are more nodes are due to the number also. And that we use our like previous we will split the area and another one conventional when coming with conventional lava, the conventional lava is in better nuclear utilization because there are so many cases. Only to transmit the coming like a successful probability in Alova Nova state. And then when coming in this figure, we have plotted versus atom rate. Here, from solid lines are above feet for R equal to 3 and R equal to 2. Up to some distance, up to some atom rate, up to some atom rate, to obtain laboratories for that. That is the number. That is the actually important. And then we found when we set the maximum memory utilization. We found for all of the capabilities, we need to these function level place, any level these are the optimal T 59. For this, the optimal atom rate is 51. For this, the optimal atom rate is 42. Only the other plates are 30. Whenever there are number of nodes are increasing, the optimal atom rate is less. I mean less. Because when high number of nodes and high atom rate is the function. That is very easy to understand. The same thing we are doing in the results. Then with the number of nodes, what about optimal atom rate? These are the number of nodes with nodes very high chance. Okay, when more after one more thing we can understand is like Aloha Noma. One more thing we can understand is Aloha Noma in all the thing with in textile optimal again, optimal again. Then this one is With number of nodes, we are checking the MAC layer utilization. When number of nodes, MAC layer utilization, some sense. Okay, is that one number of less. So now we graphically remove. Slowly, it is really that for some kind of for some nodes. After that, if the nodes are increasing, manually utilization increases. Here the observations are like results show that post alpha scheme improves the MAC utilization and improves the comparative alpha scheme. Like coming to the conclusions, we have investigated the performance of NOMA integrated with the half duplex cooperative relay scheme in for underground professional sensor networks, considering the practical limitations of imperfect CNC and imperfect SNC. What will the proposed NOMA CRS demonstrated recording something under the ASP concept. Subsequently, we admit that fully meaning relay scheme for viewing results in incorporating the effects of self-interference and the imperfect SNC. Here, Fullmetrics is giving enhanced ergodic rate and the lower outage probability comparing to the existing schemes. Sir, sir, in the next thing, our aim is to address the energy. To address the energy constraints in underwater environment, we presented an enhanced script to NOMA model, demonstrating its potential to significantly improve the energy efficiency in UASs. Finally, we have proposed a novel NOMA-based alpha protocol for back layer enhancement in UASs. And the result is like proposed alpha NOMA yields notable improvement in back layer utilization, network throughput, outperforming the conventional. These are the references. Any queries? Welcome.
Aloha can be can present for 60 communication.
So basically, this Aloha is not that much MAC layer utilization scheme, sir. And CSMA and all will do better than Aloha. But there are some situations like satellite communications where there is a longer propagation delays are there. That time is carrier sensing is somewhat inefficient, sir. Similar like that in underwater also the propagation delays are very high, so that carrier sensing is not efficient. It is inefficient. Due to is the one people who are using in underwater acoustic sensor networks. That's why we have used Aloha with the NOMA sensor.
So, what are the practical limitations are there in underwater as compared to the traditional?
Resources are resource constraints are there. Like power is the one thing because here sensor nodes are battery powered. In terrestrial, we can change the nodes whenever it becomes dry, battery dry. But in underwater, it is very difficult. And the channel constraints is too much complex channels, time varying channels are there. And when coming to the RF signals, we cannot transmit for the longer distances. Optical also we cannot transmit for the longer distances. How we are getting in terrestrial sensor networks.
Thanks.
Thanks. Thank you, everyone. Yes.